bit of technical difficulties at the start of class, like always. So this is convex optimization. If you guys are in the wrong class, I won't feel offended if you want to hop out now. Just to give you a few details about the course, somebody told me that the best courses have the shortest time spent on administrative stuff, so I'm going to try to keep that pretty short. I'm your instructor, Ryan Tibshirani. I'm in the statistics and machine learning departments. We have some great TAs this semester. Mattia, Nicole, Biru, and Yu Sheng. Do you guys want to stand up so they can see you guys? See Mattia, Nicole. I don't see Yu Sheng or Biru. I know Biru's away. We have a special guest lecturer who's going to participate in the course. His name's Javier Pena. I'm going to refrain from calling him an instructor because I don't want you guys to go to him for questions or administrative stuff. That's why his name's not here, but he's gonna do us the favor of giving us a few guest lectures this semester. Here's the course website. You can find all the homeworks, the schedule for the class, the lecture notes. Mostly everything is on this website. The other thing we'll use for class discussions is Piazza. So I think Nicole has enrolled most of you guys in the Piazza system at this point, but if you're not, then you can go ahead and sign up. There's a link off the course website. So try to keep all the class discussions, all the questions, everything, try to keep that to Piazza. It's going to make it a lot more manageable for us to answer your questions. And we think it's going to be a good forum for that. So Piazza and then the website, those are your kind of two main sources of information. So there are no formal prerequisites for this class. I don't think you have to have taken any class to be enrolled. But the class is going to be fairly fast-paced. So we're going to assume that you know the following topics, and then you can kind of work with them. Real analysis, calculus, and linear algebra at the level of, say, a PhD level machine learning course. Core problems in statistics and machine learning. So in this class, we're going to talk about optimization algorithms. Our focus is going to be on statistics and machine learning problems. If you didn't know those problems in the first place, if you didn't know why we were trying to solve them, it might be hard to understand the algorithms for them. So we're going to assume that you're familiar with problems like regression, penalized regression, classification, etc. You have to know how to program. The language that you want to program in, we're not going to be so particular about. So we're going to support the languages MATLAB and R. Our TAs, between the four TAs, we have TAs that are experts in MATLAB and experts in R. If you want to program in Python, that's fine with us. If you want to program in some really obscure language that we've never heard of, then maybe check with us before you do the homework to make sure that we can understand your code. But we're pretty flexible on the language to choose. Like I said, we'll support MATLAB and R. So if you have problems in either of those two languages, we can help you. We're going to assume that you're familiar with basic data structures and computational complexity arguments like the running time of an algorithm, order notation, that kind of thing. And formal mathematical thinking, that's kind of very broad, but I think as we go through the first several lectures, you'll see what I mean. So if you don't feel like you're comfortable in any one of these things, that's okay. You can still catch up. Don't hesitate to talk to us, though, because we don't want you to fall behind early, be lacking in some key area, and then find it really hard to catch up in, say, the third or fourth week or something like that. Okay. What are you required to do in the class? We have 6 homeworks. So there's going to be roughly 6 units where we cover 6 different bundles of topics. There's going to be one homework for each of those units. We're going to have one midterm that's in class, one little test. So I've started calling it a little test because it is an exam towards the end of the semester, but it's supposed to be very easy, and it's small, so we're going to call it the little test. And you're going to have one project that if you're enrolled for 12 units, you have to do the final project, the course project. If you're enrolled for 9 units, you don't have to do the project. So that's where the difference in the units are. It's up to you. And this is something new this year. You're going to have many easy quizzes. And to stress how easy they're going to be, we're going to do one together. The first quiz we're going to do together at the end of this lecture. So we'll go through it together. The first quiz you're not going to have to do. But you'll see how easy they are. What's the setup is going to be is that after each lecture, we're going to release a quiz. That quiz is going to have about 8 questions on it. They're all multiple choice. It's on the web. And it's due at midnight the day of the lecture. So the first quiz would have been due today at midnight for all of you guys. 8 multiple choice questions. But we're going to do it together, so we're not going to count it. And the way the quiz works, it's some nice software that's written by Jeff Gordon, who's a faculty member of machine learning. It's a system where you can take the questions in the quiz as many times as you want until you get them right. If you get them right the first time, you get full credit. If you get them right on subsequent tries, you get half credit. So it's a very kind of relaxed quiz system. It's supposed to be just checking, did you go to the lecture or did you even flip through the lecture notes? Are you on track? So you shouldn't stress out about those. Scribing. Scribing is not technically required, but we find that it helps students a lot. It doesn't really do much for us as the instructors, to be honest. Right? Scribing is for you guys. You guys can have kind of a summary of each lecture. And the way we're going to make it work this year is that you can sign up for scribing on the course website. And you're allowed to scribe once per semester, and there can be 2 or 3 people who are scribing each lecture. And it can bump up your grade in boundary cases. So if you had a B+ at the end of the semester and you're right in the boundary, and you look back and you scribe, we'll bump you up to an A-. Okay, so it's going to be extra credit for people on the boundary cases. It's worth doing it. It helps you understand the lecture. And we think it's beneficial for you guys, so go ahead and sign up to scribe. These lectures are going to be videotaped, and we're going to post them on the course website. These are supposed to be supplements, not replacements, for actually attending the lecture. So I definitely encourage you guys to come. It's a lot more fun when the class is full. It's very full today. I'm not sure we get any more full than this, but I wouldn't skip out on the actually attending the lectures just to watch the videos. It's much less fun. Auditors, if you guys are postdocs, faculty members, students from other departments, whatever, if you want to audit the class, that's totally fine with us. Please just sign up officially for an audit. It helps out the department. All right, and the most important rule, which is not really a rule, just a motto, is to work hard and have fun. Because I think optimization is a really fun topic. It's also a challenging course, but you'll get a lot out of it, we hope. Are there any questions before we start with the lecture?
Since there are more people than seats, how will people on the waitlist be prioritized?
That's a good question. So we have a lot of people on the waitlist. We're going to basically descend in order. So the waitlist has an order. We're going to essentially move through an order. The reason I say essentially is that we're going to give preference to people in statistics and machine learning. That's it. So we've managed to get most people in those 2 departments into the course. I think there are a few still on the waitlist. After they get emptied from the waitlist just moves in order. You can always come talk to us about how likely you think, or whether we think it's likely that you'll be able to get into the course offline. Although we can't really say. But if you're towards the end of the waitlist and it's 70 large, then it's probably unrealistic. Other questions? All right, that was pretty good. I think that was about 10 minutes or less. So let's get to the fun stuff. This lecture is going to be mostly non-technical, just kind of motivating the course. We're going to see a very important result at the end that we're going to actually prove together. It's a fundamental result for optimization problems, in particular for convex optimization problems, but it's simple enough we're going to prove it at the end together. So in past years I've tried to do this motivation, like optimization problems are everywhere in every facet of life, but the truth is that I'm not really an expert in fields outside of statistics and machine learning. So I can really motivate optimization problems for these 2 fields, and that's what I decided to do now. They really underline most everything we do in these 2 fields. In many other courses, you might learn how to translate a conceptual idea or goal, like predict y from x, where y is, say, binary, into some kind of optimization problem. So the machine I build to predict y from x is built by solving an optimization problem of the form minimize some function, f of x, overall values x in some set d. In other courses, you learn how to do this translation. You've seen that a lot in 701, say. And if you, in stats, you might see that in 707. This course is going to teach you how to solve P, this problem, and also why it's important to solve this problem. Okay, so we're going to kind of dig into this idea of there's an optimization problem we want to solve. We're going to open up the black box. We're going to figure out how to solve this problem. We're going to see that there are many ways to solve this problem generically, especially if the problem is convex. And we're going to find that there are a lot of important things you get out of just solving it. It's not just to get the solution. You actually learn a lot in the process. So let's start with some examples of this translation. What are some problems that you guys have learned in other courses that are, say, some kind of statistical goal that are translated to optimization problems? What do you guys think? Yeah.
Maximum likelihood.
Yeah, that's a great one for, especially for the statisticians. Maximum likelihood. Right. So in this problem, we write down an error model for the data, right? With some kind of data generating distribution. And in this case, it's not always about prediction. It's about parameter estimation usually. We want to understand some parameters of that distribution. And we do that by maximizing the likelihood. Okay, that's a kind of core statistical topic. That is an optimization problem, obviously, right? We're maximizing some function. That function is the likelihood over the parameter values that govern that likelihood. Right, so that actually captures a lot of specific subcases. So what are some subcases of maximum likelihood that are kind of more concrete than just this general case?
Least square problem.
Right, least squares problem. So, we'll call it linear regression. Another one is logistic regression, right? So these are both cases of maximum likelihood that we do depending on the error model for our data. We perform linear or logistic regression. One is for predicting or parameter estimation for a real valued output. The other is for a binary output. What are other examples of optimization problems? There are tons. I mean, it doesn't have to be fancy. What do you guys think? Yeah. Principal component analysis. That's a good one. So this is not for prediction, right? But it's to do, in a sense, it's to do subspace estimation for our data. Right? So we're casting the problem of finding a subspace that has high variance as an optimization problem. And I think we'll actually visit that problem in a couple of lectures. And we'll, of course, visit linear and logistic regression in various flavors, penalized flavors soon as well. Other examples? Yeah. Yeah, that's a good one. It's an algorithm typically, or an optimization problem typically to build classifier. Doesn't usually come with an error model for the data, so it's just kind of outside the maximum likelihood scope generically. But it's an extremely popular and well-studied problem for classification, mostly in machine learning. Yeah.
Kernel density estimation.
Sure. Yeah, that one's actually a little bit interesting because we'll put a question mark next to this. What problem is that solving? What optimization problem is a kernel density estimation solving? Kernel density estimate solving? Okay, so that's a little bit different than actually the kernel density estimate. Let's suppose I had the kernel density estimate, and I just chose, I had the bandwidth chosen, like I chose the bandwidth to be 1 or something, and I wanted to do density estimation. Is kernel density estimation solving an optimization problem, or is it just a procedure? What's that?
Probability density that is estimated in the distribution.
Correct, but what is it, with respect to what problem is it optimal? Can you write down a criterion that the kernel density estimate is minimizing? It's unclear, right? So, in a sense, statistically, kernel density estimates are equivalent to a different type of estimate asymptotically. That other estimate is solving an optimization problem. They're called smoothing splines. So it kind of is solving an optimization problem, but that's not really clear in finite samples, right? So this is not really solving an optimization problem. It's just a procedure. Do people understand the distinction? So each of these, let's say linear regression, I choose the coefficients in linear regression to minimize the least squares loss between y and x beta. So beta is optimal with respect to that problem, right? It minimizes the squared error between y and x beta. Same goes with all of these. Kernel density estimates, I don't write down a criterion that these minimize. These are just given by actually, I pick a kernel, I pick a bandwidth, and it's a closed form expression for the density estimate at any input.
Yeah, there was a recent paper that showed that the KDs was solving the least squares error problem of kernel median beating the Walla points.
Okay, so that's maybe why I put a question mark. I think there are some ways to write this problem to make it sound like an optimization problem. Maybe the one you suggested is better than the example I had, which said that it's equivalent in some sense asymptotically to another one. But I think we can think about this also mostly as a procedure. Right? I'm trying to find examples to the contrary. So that was my lead-in. What are examples of the contrary? So these are things we do in statistics and ML that aren't optimization problems. The KDEs, I guess, are kind of on the fence. I'll give you a hint. How do we, let's say I have a classifier. I want to estimate its misclassification error out of sample. How do I do that with some data? Fixed classifier, I just want to know what its misclassification error is. Cross-validation, right. So is cross-validation, does the cross-validation estimate itself solve a particular optimization problem? Is it optimal with respect to some criterion? Not really, right? It's just a procedure. So it's the same thing. It's not really solving an optimization problem. Cross-validation, just for a fixed classifier, is just a procedure that we kind of know and trust to estimate its test error. So that's misclassification error for a classifier. Okay, and there are many other examples of this. For example, the bootstrap is another thing that we do commonly in statistics, and increasingly so in machine learning. And it provides us estimates for inferential quantities like confidence intervals. We can also use the bootstrap to estimate the misclassification error of a classifier. But it's not optimal with respect to some criterion. It's just a procedure. So there are certainly examples of problems that we solve in stats and ML that aren't kind of optimization problems, or procedures we use that can't be cast as optimization, as solutions of optimization problems. But it's much more common to look at these guys, right? I think people are a bit shy, but I think we could probably continue on with another 20 examples of things that we do in these fields that are optimization problems. But we would have a harder time thinking of things that we do that aren't optimization problems in these fields. Okay. All right. So presumably other people have figured out how to solve these problems, right? Obviously, we're not the first to think about solving optimization problems. Statistics and machine learning are, in a sense, users of optimization. Classically, they're not developers of optimization techniques, right? That itself belongs to other fields. So other people have figured out how to solve these problems. Why is it important to us? Why should we bother? Well, here's two reasons. I think that there's a kind of two major reasons, but there's more. These are the ones you can think about for primary motivation. The first one is that different algorithms can perform better or worse for solving different problems. And this difference can sometimes be drastic. We're going to see an example of that in the next few slides. So if you understand the situations in which some algorithms work better than others, then you can actually, in practice, solve these problems more efficiently. Right? You wouldn't pick algorithm A to solve a problem if algorithm B you know is kind of better suited to the characteristics of that problem. And the differences between algorithms A and B can be enormous in practice. So that's why it's important to understand the landscape of optimization algorithms when you're looking at any particular problem in your research. Here's the second reason. It's kind of less obvious. So this one I think you could have guessed, right? Different things perform better or worse. We have many tools. We need to figure out which tools to use when. The second one is a bit less obvious, and that's the following. Studying this problem can actually give us sometimes a deeper understanding of the statistical problem that we're interested in. So this is where the optimization theory, or the optimization techniques, have kind of a feedback loop with statistics and machine learning. So understanding optimization can actually enable us to make more statements about the statistical problem that we're interested in. And we're seeing more and more examples of this as the fields of optimization in stat and ML kind of move forward. And I'm going to give you an example of that also in this lecture, so you can see what I'm talking about. So just a word of advice, or a word of warning, I guess. Optimization is a very current field, so that makes a lot of people feel intimidated by it. You know, you might think, wow, I really understand these cutting-edge algorithms. I get it. I get the whole landscape. I understand everything. And next year, say at NIPS, somebody could say, hey, I have this algorithm that's better than all the ones before, has a new convergence rate, It can solve problems in a different regime, and you might think, shoot, it moves so quickly, I couldn't catch up. So it can be intimidating in that sense, but I think that actually that makes it very exciting. And that makes it worth keeping up with optimization, because there's still much room for progress. It's not an old field that's kind of done. It's not like calculus where people don't really develop calculus tools anymore. It's something in which there's still very much room for progress. And that's especially true at the intersection of stat and ML. That makes it very exciting to study. All right, so here's our first example. We're just going to kind of peer at this problem, peer at a few algorithms to solve this problem, and we're going to see that they perform very differently. So this problem is called linear trend filtering. And the setup is that suppose I have observations yi, and for simplicity, I'm going to assume that I observed yi at some underlying position xi, where xi is just equal to I. So across the evenly spaced positions 1 through n, I observed y1 through yn. Okay, and so let's suppose these were the sequence of observations that I made. The y's were just the height of these dots here, and x is along the x-axis. Okay, so across 1 through 1,000, you can think of these as time points. Across times 1 through 1,000, I observe measurements of yi. So linear trend filtering is an estimator that we might use if we believe that the sequence of observations that we're looking at is well approximated by a piecewise linear function. So we might think a priori that it would be a good idea to estimate the sequence by a piecewise linear function. Okay, so how do we do this? Well, we can do this by solving an optimization problem. And this optimization problem, I think, is a clever one. It's also simple enough that we can understand, so that's why I chose it. The problem is to minimize the following criterion over all values of beta. So I'm going to estimate one value of beta, so beta I, for each observation yi. And I'm going to do it by minimizing this criterion. The first term in the criterion, there's two terms, is the least squares loss between each yi and beta I. So this is just saying that I want the points I estimate beta I to lie close to the measurements across all time points. So you guys have surely seen that in other examples, other courses. There's a second term though, and this term is what gives us the piecewise linearity of beta. And that adds up for all I, so basically over all time points, the absolute value of beta I minus 2 beta I plus 1 plus beta I plus 2. And there's a parameter lambda that multiplies this term. Lambda is a pre-specified real number that we choose. It's positive. So think of lambda as like 20 or something. Okay? So for those of you that are familiar with the lasso, or say L1 penalization in other contexts, which we'll see in this class also, you might recognize that by solving this problem for a large enough value of this parameter lambda, if I make lambda large, I'm going to enforce that many terms in this sum are exactly 0 at the solution. So I will get, right, the fact that I use that penalty tells me that for linear trend filtering, I will have beta I minus 2 beta I plus 1 plus beta I plus 2 equals 0 for many I. And the larger I make lambda, the more i's for which this is true. Okay, which i's for which this happens is chosen adaptively in a sense as we solve the optimization problem. So as we make lambda large, more and more of these terms get set to 0, but we're not explicitly controlling that. We're not telling this problem that we want to set it equal to 0 at I equals 10, right? It just comes out of solving the optimization problem. What does this mean? If beta I minus 2 beta I plus 1 plus beta I plus 2 is 0, that's equivalent to saying that beta I plus 1 is equal to beta I plus beta I plus 2 over 2. Right? Which means that beta I plus 1 lies in the line that's defined by its neighbors. So in other words, there's a single linear segment between beta I plus 1, and beta I plus 2. So the larger we make lambda, the more linear triplets we get. Right? So if I make lambda really large, and this is 0 at a bunch of places, then I'll get something like this, okay, where I'm plotting the solution here for lambda equals, I think I just chose some value for visual purposes, say 20. And you can see that beta I plus 1 is exactly equal to the average of its neighbors, and for all I between 1 and approximately 200. And then at 200, I get the property that beta I plus 1 is not equal to the average of its neighbors. Right? Because for that particular value, it was important to minimize the data fitting term, this loss term, to make a break in the linear segment. Okay, so this is the solution to this optimization problem that I'm plotting as a blue line for some value of lambda. Okay, so it's nice. It gives us a nice estimate of the underlying trend. How did I get this? Well, I chose a particular method that we'll learn in class called the primal dual interior point method to solve this problem. And it was very, very fast for this problem. There were 1,000 data points here, which is not a huge problem, but it's not small either. So it's, the problem is 1,000 dimensional. And this interior point method took 20 iterations. It was very fast. It took, a fraction of a second on my laptop. I chose another algorithm that you may have heard of that we're going to learn as well, spend some time on. It's proximal gradient descent. And starting at the same point, at the same place as the interior point method, the same value of lambda, the same data, everything. I'm trying to just solve the same problem. I spent 10,000 iterations of proximal gradient, and that's what I got. Okay, and if we evaluated the criterion of this red guy versus the criterion of the blue guy, we see that actually the red guy is very far from optimal. So I didn't come anywhere close to minimizing the problem. So it was not a good choice in hindsight. Right? I would need, in this case, hundreds of thousands of iterations to get something to look like this. Here's a third algorithm, court descent. Court descent is extremely popular for L1 penalized methods. And again, we'll learn in class. And I spent 1,000 cycles of court descent. Each cycle is a pass through each coordinate. So it's 1,000 coordinates. This is 1,000 squared iterations in some sense. And this is what I got. I got this thing in green, which is even farther from optimal than this thing in red. So this, if we plug in this into the criterion, we'll see this criterion value achieved by this blue fit is way smaller than this red one, which is in turn way smaller than this green one. So the blue thing is closest to optimal. Okay, so all of these algorithms perform very differently, even though there's nothing wrong with them. And you can see that, we'll see in the class that each of them are extremely useful in their own right. It's just that for this problem, it happened that the interior point method was the best choice. And in case you're confused later on, we'll learn all these methods. You might go back to the slide and say, hey, how do we do this on this problem? We first derived the dual problem of this, and then we applied all these algorithms. Okay, so that'll make sense later on. If it doesn't make sense now, that's totally fine. All these were applied from the dual.
Can you usually look at a problem and guess which method would probably work better than others?
That's what we're going to try to get you to develop in this course. So essentially that. And the answer is yes, roughly. I mean, I'll explain in the next slide why you might have guessed that the interior point method was appropriate for this particular problem. Okay, so we've kind of already said this, but what's the right conclusion? Is the right conclusion that we should never use proximal gradient or court descent and always use the interior point method? No, that's not the right conclusion. Those are all perfectly good algorithms for different situations. We're going to learn lots of details throughout the course so that you'll be able to develop intuition. But here's what the kind of intuition was going to be for this problem. The primal dual interior point method was fast in this case because the primal dual interior point method, in general, reduces to solving linear systems in the Hessian of the loss function. So once we go to that problem, that'll make sense. And in the trend filtering problem, those linear systems were very structured. Okay, so instead of solving like a big dense linear system, we were solving, in fact, banded linear systems here. So it's very easy to do that. So had you looked at the problem and written down its Hessian, you would have seen, this is banded. I can probably use an interior point method, which would have fast iterations because of the structure there. Proximal gradient is slow here because of conditioning. So actually, this problem is extremely poorly conditioned. If we look at the Hessian, again, then we'll see that it has a huge largest eigenvalue and a tiny smallest eigenvalue. So it's very poorly conditioned, and that really hurts proximal gradient. Okay, so again, we might have had a sense for that had we known the strengths and weaknesses of proximal gradient after we just looked at the problem and written down its Hessian. Court descent is slow here for a trickier reason. And it's a little more subtle. When we get to it, this particular topic, we'll go through this in detail, but coordinate descent can be fast if something that we call the active set is kept to be small. So coordinate descent iterates over an active set of variables. These are variables for which, in a sense, the solution is dictated by the presence of these variables, and the other ones don't matter so much. In this case, you would see that from the dual, the active set is huge. So actually, it's just really hard to use coordinate descent in this case. Okay, so we'll come back to this problem later in class, and I encourage you as we go through these algorithms in class to come back to this first lecture and see if this makes sense to you. But that was the rough conclusion. Any questions about that? Yeah.
But frame the problem as you mentioned, where we traded off for the extent of linearity. Why couldn't we instead say that? Well, I'm actually asking a question about framing the problem. I don't know if that's the ambit of this course. But say I know I'm going to take piecewise linear parts, and I'm going to say I want to change my knee points around, and I'll have parameter based on the number of knee points I'm going to have.
So yeah, so to first answer your meta question, yeah, it's not the intent of the course, but I do welcome questions like that, because this is a stats and ML course, so I want to talk about stats and ML problems. So if it ever gets to the point where we spend most of the lecture on a kind of statistical question, then I'll probably change focus, but there's no problem asking those types of questions. And then to get to the actual question, that's a way to do it. So I could say that, I have parameters for change points, I'll estimate them, and then between them I'll just fit a linear segment. That problem is going to be hard to frame in a convex way. Okay, so in particular, the locations of those change points are discrete, right, because I have discrete data points. So that's going to already make things hard. This kind of does it automatically for us. So the change points here are dictated by the size of lambda, and the locations are chosen to best fit the data. So it kind of does it in a way that seamlessly takes care of this problem. I'm not sure that we'll revisit this particular estimator trend filtering in detail, but if you want to read more about it, there are some references there, and it has quite nice statistical properties. And does it automatically. Good question. Any other questions? Yeah.
So in the comparison that you showed, you kept lambda the same for all three methods.
Right.
But the objective was basically to get something as close to linear while minimizing the least square objective. Does it make sense that different methods would do better with different lambdas?
That's a great question. That's absolutely true. So lambda here affects the conditioning of the problem. And it also affects the size of the active set for coordinate descent. So yeah, it's true that for different values of lambda, these algorithms perform differently. I chose a value of lambda that was statistically reasonable, right? We know that when solved properly with this value of lambda, we get an estimate that's statistically reasonable. So I said, let's suppose we're interested in that. In that case, for this particular problem, the interior point method was, in a sense, the best choice. If we made lambda a lot smaller, if lambda was very, very small, then what would happen in this problem is that we get a lot more breakpoints, right? And the strength of the linear penalty will be reduced, so we'll be kind of enforcing linearity a lot less. In that case, coordinate descent will actually be better. So, yeah, it matters.
So in a lot of optimization problems, we end up with something like this. We have some variables we're trying to optimize and some hyperparameters that we select. And sometimes people try different values for these hyperparameters. I always wonder why we don't just include them in the optimization problem.
Yeah, that's another good question. So the question to rephrase it was, why aren't we including lambda as an optimization parameter? Well, again, my answers might start to sound repetitive, but it's hard to do that in a convex way. It's typically very hard to make the problem convex if we're optimizing over the tuning parameter and the variables themselves. Okay, we're going to see the importance of convexity in the next few slides. But we will also consider the problem of tuning parameter selection in this class just from the optimization perspective. We'll see that actually we can solve over many values of the tuning parameter and do it using warm starts, which is a term for basically starting the optimization algorithm at one value of lambda at the solution of the previous one we solved. So it helps us solve kind of this problem over a grid of lambda values very quickly. Yeah?
So in this situation, how are the betas initialized?
0. All betas are initialized at 0. Yeah. So just a line on a straight line in this plot. All good questions. All right, so here's a second example. So that was an example of how different algorithms can work better or worse depending on the situation. Here's a second example. This one is how kind of studying the optimization problem in its guts from the perspective of optimality and all the things we know about it can give us something statistical that we may not have known before. So the same problem, and we've already kind of just discussed this. When lambda is really big, we see very few breakpoints because we really penalize deviations from linearity very strongly in that optimization criterion, right? As lambda decreases, we get more breakpoints. So these are changes in slope in that solution, which I'll write as beta hat. That's the solution to this problem. So when lambda is 20,000, I guess I was off with my scale. I told you it was 20 in the last slide. I probably chose it to be 1,000. When lambda is 20,000, you can see that we penalize deviations from linearity very, very heavily. Right? We penalize changes in slope very heavily, and so the solution looks like this. When lambda is 1,000, the solution looks like this. When lambda is 10, the solution looks like this. So I don't know how well you can see from the slide, but this one has a ton of breakpoints. Okay, so we might ask ourselves statistically, along the lines of the question that was just asked, what's the right value of lambda? How can I determine what the right value of lambda is? Well, here's a very specific way that we might attempt to answer that question. As we move along, we may want to get what's called a p-value for the presence of a breakpoint. So we'll test the hypothesis that as I introduce a breakpoint, that breakpoint is statistically significant. I'm not going to give you details on what that means precisely. It's kind of beyond the scope of this example, but this is work that's, I think, currently popular to pursue in statistics and machine learning. So let's learn a little bit about the problem. The values of lambda at which the solution beta hat exhibits a new breakpoint as we decrease it are called knots. So as I make lambda 20,000 versus 20,000 minus epsilon, it's not always the case that as I decrease lambda between those two values, I get a new breakpoint. They just occur at some values of lambda. Okay, so it might have been that at 1,000, I get another breakpoint, and then at 557, I get another breakpoint, etc. Okay, but in between those, I don't introduce breakpoints, I just kind of change the slopes of all the segments. So those values of lambda are called knots, and we write them like this. Lambda 1, which is the value of lambda at which we have one breakpoint. Lambda 2, which is the value of lambda at which we have two breakpoints, and so on and so forth, and they're decreasing. And right, the natural question is, when have we made lambda small enough so that we mostly capture kind of true structure without picking up spurious trends? It's just a very, this question is framed not specifically in a statistical sense, but I'm just trying to get the point across. Okay, so we can actually learn a lot from examining the KKT conditions here. These are a set of optimality conditions that govern the nature of the solution, and we'll go through that in detail. We'll have a whole unit on the KKT conditions, essentially. And for this trend filtering problem, they actually present to us a very natural statistic that we can use to evaluate the hypothesis that is, at the value of lambda I'm looking at, where a breakpoint was introduced, is that breakpoint statistically significant? They come from studying the KKT conditions. So this is an example where if you knew optimization and you were comfortable with it, you may be able to develop a new statistical tool. It's not about solving the problem anymore. We already have algorithms for solving linear trend filtering. I actually want to do inference, statistical inference for this problem. And it comes from understanding the optimality criterion for this problem. Okay, so again, lambda 1 is this big value. We decrease lambda, and each time we decrease it, we get another breakpoint in the solution. It turns out, roughly speaking, that if there's a big gap between lambda 1 and lambda 2, or if there's a big gap between lambda 2 and lambda 3, etc., the bigger the gap, the more significant the thing is that we introduce. So in this case, we introduce a breakpoint at lambda 5. That was our fifth breakpoint. The next value of lambda 6, at which there was a sixth breakpoint introduced, there was not a big gap between these two values. So that's statistical evidence against the significance of the fifth breakpoint. Okay, and this can be made precise as a statistical test. But if there's a big gap, say between lambda 2 and lambda 3, that's statistical evidence that the second breakpoint was important, in a sense. Yeah.
How do we decide whether the gap is big enough? Is there a threshold, or do we do something relative?
Yeah, so there's a particular statistic we form that's based on the gap, and we compare it against a null distribution. So it's in the form of a kind of a classical statistical hypothesis test. So here's the p-values from our previous example. You can see that the first two p-values are essentially at 0. Okay, so I actually ran this on this example that I showed you. The first two p-values were essentially at 0. And actually, I'll tell you the first two breakpoints that are produced, they were this one and this one. So they're really significant. The third breakpoint, the third p-value we see, corresponding to the third breakpoint is like 0.8, essentially. Why is that? And then the fourth one is essentially at 0. Why is that? Well, if you look very carefully, see if I can do this without screwing up, you'll see that actually there were two breakpoints here that the optimization algorithm shows. The third one introduced was this one. The fourth one introduced was this one. Okay, so actually when we post data fitting, when we ran this p-value test, we saw that one of them wasn't significant. Okay, so that was very useful. Right, we had 4 breakpoints. 1 and 2 were very significant. 3 was not significant. 4 was. That's why you saw in that p-value plot, right, the third p-value being very large, and the fourth one was small. Okay. Yeah.
So how did you get the lambda in the first place?
The lambdas at which these. That's another good question. So I'm not sure whether we'll cover this in this course. We have the end of the course is a bunch of advanced topics, and we'll just kind of do it based on interest, class interest. But the way I solved it was using what's called a path algorithm, which tells me exactly the values of lambda at which the breakpoints occur. So depending on interest, we might cover that as well. That came from another algorithm. Yeah.
So when you say that the third point is not significant, whereas the fourth one is, I could as well say that the third is significant and the fourth one is not, right? How exactly did you decide that one of them is and the other is?
So I didn't personally decide. This came out of the statistical test. Right? So I'm just reading off. But yeah, I mean, it's a good point. If I reran this on a different data set, it may have been the reverse. But I guess the point is that, if I look at... All right, let's start again with the lecture. I used to have a duck whistle, by the way. So when I taught this large undergrad course, I used to have a duck whistle that people have for hunting. And I used to blow it at the start of these periods. And my voice is not very loud. So I may have to bring this duck whistle back to reinstate that. Okay, so we've seen 2 examples of why optimization problems are important, in a sense, why we should study optimization. Hopefully I've convinced you, at least in part. Now we're going to see a central concept. So there's another word in the title of this course, and that's convex optimization. And so why is convexity important? And here's a little bit of history, and if I say anything that's totally bogus, Javier can jump in and correct me. But as far as I understand, historically linear programs were the focus in optimization. Okay, so a while ago, people were really concerned about solving linear programs, and they came up with algorithms to do that fairly well. And then the distinction between problems that were easy and hard was initially thought to be, is the program a linear program, or is it a nonlinear program? Okay, but then people started to find out that some nonlinear programs were much harder to solve than others. So this division between linear and nonlinear didn't really seem appropriate, because linear were pretty much all easy, and then nonlinear was a toss-up. Some of them were easy and some of them were near impossible. And so now it's kind of uniformly accepted, I'd say, that the right distinction is between convex and non-convex problems. So between a problem that we can solve and understand and ones that are kind of more we can solve and understand on a case-by-case basis. So convex problems, we're going to see we have many algorithms for them, and generically we can solve them with one of these algorithms. We can understand them from the perspective of the KKT conditions. We're really kind of all good when it comes to convex problems. Non-convex problems we're not really going to focus on in this course. Again, depending on interest, we have a set of advanced lectures at the end. I may do a lecture on non-convex optimization. And you'll see that there are some kind of generic tools, but they're not nearly as rigorous, in a sense, as the convex ones. And we understand and solve non-convex problems more on a case-by-case basis. Okay, so this particular non-convex problem, we have a good understanding of it. We can solve it. But this other one, which may look pretty similar to it, it may be too hard for us. And so now's a good time to bring up your supplementary textbooks for the course. We don't have any required textbooks. The lecture notes should be pretty self-contained. And at the end of every lecture, I'll put down some kind of references and more reading for you to look through, if in case you want supplementary reading. The ones that I would highlight kind of in advance as really good supplementary textbooks are this Boyd and Vandenberg book on convex optimization. It's available freely online, so just type in convex optimization Boyd on Google and you'll find it. Legally, it's not illegal to have this book. I think people can probably find any book that I list here in another way. This one is a very kind of broad introduction to convex optimization that doesn't focus on all of the mathematical details that we'll have in this course. So, for example, a huge thing that we study in this course is going to be subgradients. They don't even talk about subgradients in this textbook, so it doesn't have everything. But it's a very, very good textbook nonetheless. Another textbook that I personally like very much, but I think would be hard as an introductory textbook, is this convex analysis book by Rockefeller. So this is a mathematical reference that is really more of a math textbook, but in a sense it has everything. So if you want to know about subgradients, that's the place to look. If you want to know about the KKT conditions in more detail, that's the place to look, etc. So I would start in Boyd and Vandenberg. If you don't find it, I would maybe look at some of the other popular ones that Javier will list at the end of some of his lectures. And then I would end up at Rockefeller if you haven't found it in those other textbooks. Or you can, of course, come and ask me or the TAs as well. But in my experience, Rockefeller has a lot of good information. It's just a little bit harder to read. So convexity is an important topic. There's really kind of two staples of convexity: convex sets and convex functions. And the next lecture, so I guess Wednesday of this week, we're going to go through convex sets and convex functions in detail. I'm just going to give you the definitions now because we're going to use them in a second to prove something. So, right, convex set is a very basic concept. I think you guys have seen this probably in other courses. What does it mean? Well, set C is called convex if I take any 2 points in the set, x and y, and I look at the line joining those 2 points, and that line lies entirely within the set. Okay, so in this example, right, I have this polyhedron here. If I take any 2 points in this set and look at the line joining them, so this is x and that's y, how do I parameterize, first of all, the line joining these 2 points? I write it as tx plus 1 minus ty, where t is a number between 0 and 1. As t varies between 0 and 1, I get all the values in this line segment. If that's entirely contained within the set, then the set is called convex. That's the definition. This is an example of a non-convex set, this one here on the slide, right? Because I took those 2 points, say x and y, and at some values of t, this line segment escaped the set. How about a convex function? I think it's also something you guys would have seen in other courses. But a convex function is one that goes right from Euclidean space to R. So convex functions, as far as we're concerned, are always real valued. So they always give us real outputs. They could take as arguments, vectors in Euclidean space, but they're always real valued. Such that its domain is a convex set. So the domain of the function, by the way, the domain of a function, it's just notation, is a set of all x for which f of x is defined and finite. So for example, the domain of the log function is positive reals. Right? I can't evaluate log at a negative real number. So the domain of the function has to be a convex set. That relies on the definition of convex sets up here. And furthermore, the function has to satisfy this property that if I take any 2 points in y, x and y, and I evaluate the function at some point on the line segment between x and y, so it's f of the argument tx plus 1 minus ty, and that has to lie below the line segment joining f of x and f of y. Right, so here's the picture. And by the way, a lot of the pictures I'll take are from this Boyd and Vandenberg textbook. So if you recognize them, that's because a lot of the pictures I'll take will be from this textbook. If I take f of x and f of x and y and f of y, and I look at the line segment joining those two, right, the function has to evaluate to some value below that line segment. That's what this definition is saying. All right, so convex sets and convex functions. Hopefully that was clear. Like I said, we'll spend an entire lecture on them next time. So what's the convex optimization problem? Well, first, we'll just write down the generic form of an optimization problem. An optimization problem is one of this form. So I'm minimizing some function f of x. We call it usually the criterion function, subject to the constraints that a bunch of functions gi of x have to be less than or equal to 0 for a bunch of I. So I could have m such functions gi. And hj of x have to be equal to 0 for a bunch of functions hj. Say I have r of these functions. That's what an optimization problem looks like in its generic form. What is d here? I'm minimizing over all values x and d. D is the domain that's common to all the functions. So I take the domain of f, I intersect the domain of each of these functions g, and I intersect the domain of each of these functions h. Right? If I had a value of x outside of that common domain, then it wouldn't even make sense to write this down, right? Because one of these wouldn't be defined. And I'll often drop this. When I write optimization problems, I'll often not write down the domain. It's just implicit. Okay, so you look at the functions and you realize that we're only going to evaluate them at points that are in their domain. But just to be clear, that's what it looks like. So that's an optimization problem in generic form. What makes it convex is the following. A convex optimization problem is one for which that criterion function f is a convex function, as we defined. That means that it satisfies that inequality right about the line segment lies above the function, and its domain is convex. Each of these gi's is a convex function too. So same thing, same condition on them. And finally, each of these hj functions are affine, which means that they have to look like aj transpose x plus bj for some constants aj and bj. Okay, so I mean you might call it a linear function in other courses. We're just going to call this an affine function in this course because of this non-zero term bj here. We're going to call a linear function one for which it's just aj transpose x, just to be a little more precise. All right, so that's the definition of a convex optimization problem. Convex criterion, convex inequality constraints, linear equality constraints. Why can I not make the equality constraints to be convex in general? Why do they have to be affine? So the answer I'm looking for is not really a very deep one. It's a bit of a, it's just like a bit of logic. So I'll give you a hint. What happens if I took a constraint that looked like hjx equal to 0, and I wrote it as two inequality constraints, hj of x less than or equal to 0, and minus hj of x less than or equal to 0. I can always do that. So those are equivalent. So I took any equality constraint, I made it into two inequality constraints. So now I have this in my problem. Rather than the equality, I have two inequalities. What are my conditions on these functions for this to be a convex optimization problem? What do they have to be? Okay, so I have to have hj convex and minus hj convex. Well, we'll see the only way that's possible is for hj to be affine. So that's why we have that particular distinction. All right, so here is the fundamental property of convex optimization problems that we're going to prove together. This is the last slide in the lecture. Then we'll take the quiz together. You'll see how easy it is, and you'll go home happy, hopefully. So here's the property. For convex optimization problems, local minima are global minima. So any time you're at a point at which it looks like locally you are doing the best you can do with respect to the criterion function, you have found the global optimizer. That's a great property of convex optimization problems. And it's not true for non-convex ones. Okay, so here's just a picture. If we have some kind of algorithm that shoots us downhill, right, always pushes us downhill, and we get to a point at which we cannot go downhill anymore, because in any direction we look, the function is only higher, right? Then if we're solving a convex problem, that means that we have the solution. So here's a picture of a convex criterion over two variables. So it's a function from R2 to R. And you can see that this point is the global optimum. It's also locally optimal, but that implies global optimality. That's not true for non-convex functions, right? So non-convex functions can have lots of local minima. So here's an example of a non-convex function in 2 dimensions. And if I extended this function out and if I drew more of the function for you, and you'll see that actually this is the local optimum, but it's not globally optimal. Okay, the global optimizer, I'm not even sure where it is. It might be somewhere off the page. There could be lots of local optima. So what does that mean formally? Because we're going to actually try to prove this. Well, we're not going to try to prove it, we're going to prove it. A local optimizer is something that satisfies the following conditions. If a point X is feasible, which means that it satisfies all the constraints that we wrote down, that's what a feasible point means, the optimization problem, and it also has to, of course, be in the domain common to all the functions. And it minimizes the criterion function in a local neighborhood around X. So that means that f of X is less than or equal to f of Y for all feasible points Y that are at most some positive distance rho from X. So if I draw a ball around X of radius rho, I look at all the feasible points in that ball. If all those feasible points are at least as big as f of as X in terms of the criterion value, then we call X locally optimal. Right, that's what a local optimality point is, a local minima. For convex problems, if any point X satisfies this, it's automatically globally optimal, which means that it's, of course, less than or equal to f of Y for all feasible points Y. Okay, so the claim is that this implies this. All right, so let's prove that. There's only a couple steps, and they all rely on the definition of convexity. So here's X. Okay, and let's draw this ball of radius rho around X. And we're given that if I evaluate the function at X, then it's smaller than or equal to when I evaluate the function at Y for any points in this ball. As long as those points are feasible, right? So there's some feasible set I'm going to intersect with this, but I'm not going to draw that as part of the picture. Let's suppose in order to achieve a contradiction, this is going to be a proof by contradiction, that there's some point that has a smaller criterion value than f of X. Okay, we'll call that point Z. I know that this point has to lie outside that ball, right? Because by assumption, I'm better than everything in that ball. So let's suppose that Z is out here, and I have that f of Z is strictly less than f of X. And of course, Z is feasible, and it's in the domain of all the functions. So now I'm going to do something where I draw a line between X and Z. So let's argue in 3 steps. First, I'm going to claim that any point on that line segment between X and Z is feasible. Okay, so I'm going to claim that Tx plus 1 minus Tz is feasible. So why is that true? Well, first of all, let's call this point, X tilde. So X tilde is going to be in the domain, I claim, common to all the functions. That's true because that domain was an intersection of convex sets. An intersection of convex sets is convex. We'll learn that in the next lecture. So if I had this point in the domain, X, and I had this point in the domain Z, then by the definition of convex sets, any point in the line between them has to lie in the domain. Okay, so that's good. What else does it mean to be feasible? I have to have that Gi of X tilde is less than or equal to 0 for all I. But right, that is just equal to Gi of Tx plus 1 minus Tz. Right, and by the definition of convexity, because G is a convex function, Gi is a convex function, this is less than or equal to T times Gi of X plus 1 minus T times Gi of Z. And each of these is less than or equal to 0. T and 1 minus T are both negative, right? So that's going to be less than or equal to 0. So, all right, great. X tilde satisfies all the inequality constraints. How about the equality constraints? Well, that one's easy, right? Because it's the same thing. Right, that's the definition of Hj of X tilde. And if we expand this out, we'll just see that's equal to 0 plus 0, right? Because AJ transpose X plus BJ is 0, and AJ transpose Z plus BJ is 0. All right, great. So X tilde is feasible. That's good. So that means that if I look back at this picture, any point on this line is in the feasible set. Now I'm going to do something else, which is I'm going to try to choose a value of t that is large enough so that I get a point inside this ball. Okay? And I can do that, obviously, by taking t closer and closer to 1. What happens if I do that? What's going to happen to that point? So we're going to choose t big enough.
We can't see that.
Thank you. If I ever get off the page, just give me a holler. Choose t big enough so that x tilde, which is tx plus 1 minus tz, is in the ball. And I'll let you, if you want to make that more precise at home, go for it. You can just find a value of t that's defined from the row, and x and z to do that. Okay, so, but at least you should see, intuitively that's possible. What happens when I do that? What's the problem now? What am I going to do? Right, so I'm going to evaluate f of x tilde. And I know from the definition of convexity that's going to be less than or equal to t times f of x plus 1 minus t times f of z. Right? By assumption, though, f of z was smaller than f of x. Right? So this is strictly smaller than t times f of x plus 1 minus t times f of x, because this was strictly smaller than that. Right? And that's equal to f of x. So in other words, I found a point x tilde in the ball that was smaller, that had a smaller criterion value than f of x, the next one. Okay, so that's a contradiction. And that proves it for us. Right? That if we ever have a point that's locally optimal, that point is also globally optimal for convex optimization problems. Any questions? Great. So I think we all got that. That's probably the easiest thing we'll prove all semester. Although I have to say that the KKT conditions in duality have very simple proofs too, but they're hard to understand.
You need to pick the t less than 1.
True. That's true. So I also need t to be t less than 1, big enough. And bigger than 0. Great. All right, so let's take this quiz, and then you guys can get out of here. And you can see how easy this is. So we're going to release this link. So you don't have to do it today. This takes care of it. But on Wednesday after the lecture, within, I don't know, minutes of the lecture, we're going to release the link to this quiz on the course website. You just go and you click on that link. It'll take you to this this particular quiz website that, like I said, Jeff Gordon wrote. You have to sign up for this website in order to use it. So if you used it for 701, I think, did you guys use it for 701? You'll just have the same user ID and stuff. If you didn't, then you just use your Android ID, and you can use any password. So I'm told that it doesn't have to be your Android password. So don't use the Android password just for safety. Just choose anything, because it's just a quiz website. It's not super important. Okay, and then once you're here, you take these quiz questions before midnight, and that's it. We'll handle everything else. So let's go through them. If f is a convex function, then the following is a valid constraint in a convex optimization problem. F of x is equal to 0. Is that true or false? False. Okay, great. Right, because f has to be affine to 1. It can't be, generically, it can't be a convex function. So unless, okay, good. So I made the quiz correctly. That one says correct. Algorithms for optimization. Basically, all algorithms for an optimization problem, for convex optimization, perform the same across all problem instances. Picking an algorithm is for a particular problem is mostly a matter of taste. False. Okay, good, because we learned that we had these 3 algorithms for trend filtering. They all work differently. A set is convex if for every pair of points their convex combination is also contained in C. Formally, this means that Tx plus 1 minus Ty is in C for all t between 0 and 1. Tx plus 1 minus Ty is in C for all real valued t's. Or Tx plus Ty is in C for all t between 0 and 1. Which one? First, second, or third? First one. Okay, so let's suppose my finger slipped. I meant to put the first one. Oh, it's wrong. Okay. So at this point, you can say, oh, okay, well, let me see. I'll try this one even. No, that's wrong too. So I go to the first one, and I click correct, and I get half credit. Okay, so that's the worst that happens. And I definitely do not want you just to go through and try everything. But it's worth trying to get the questions right, but not supposed to be hard questions. A convex function must be defined on all of Rn. Is that true or false? False, right? Because we said that a convex function could have a domain. I wrote that down here. Linear trend filtering. The objective, or the loss term in linear trend filtering, encourages each coefficient to match the observed data. So this is where you might say, I forgot what linear trend filtering was. You go to the lecture notes. All right, go back to it. That's the loss term. It encourages each coefficient to match the observed data. Coefficient means beta I here. That's true, right? That's the point of that term. Try and make beta I match yi, the least squares loss term. The penalty or regularization term in linear trend filtering encourages each coefficient to equal its neighboring value, each coefficient to equal the average of its neighboring values, each coefficient to equal 0, each coefficient to lie in a line segment through 0. Which one? The second one, right?
Yeah.
So it's not encouraging the neighboring value. That would be beta I minus beta I plus 1. Right? It's not encouraging them to be equal to 0. And it might be a bit tricky between B and D, but if you look back at what we wrote down, right, that's exactly what it's doing. It's trying to make each coefficient equal the average of its neighbors. Great. In a convex optimization problem, any local minimizer is automatically globally optimal. True. Yeah, we proved that. The last one, for a point x to be considered feasible with respect to a given convex optimization problem, which of the following need not be true about x? X is in the common domain of all the functions. X minimizes the objective. X satisfies all the constraints. Second one, right? Yeah. That's the definition of a solution, if it's feasible and it minimizes the objective. All right, so that was it. That should take you, I'd say, 10 minutes maximum. I mean, and like I said, you don't get penalized too heavily for having the wrong answer the first time. So I guess we'll see you on Wednesday then.